Welcome, everybody, to the next edition of our MathWorks mini-series. We're going to go ahead and kick it off in just a couple of minutes with Abhishek Shankar from MathWorks as we talk about designing and deploying state machines with Stateflow. But we're going to just make sure we allow some time for everybody to join us this evening. So again, we're just going to get kicked off in just a couple of minutes. We'll be right back. Welcome, everybody, to our next edition of our MathWorks mini-series. Today, we are discussing designing and deploying state machines with Stateflow. They're useful in developing our autonomous systems. I know many of you are joining us from our RoboBoat, RoboSub, RobotX, SUAS, and more communities. And we're really excited to welcome all of you guys. As a reminder for those of you who aren't part of our programs, RoboNation is a nonprofit organization. We actually oversee 9 different STEM-related programs, everything from the K-12 space with a program called CPERSH all the way up to some of the ultimate sides of robotics with a program that we host called RobotX. We're really excited to welcome all of you here. Please learn more about us on our website, robonation.org. And this is a webinar that's for folks that are interested in all different aspects of STEM. And so we consider ourselves a robotics community. So whether you're a participant in one of our programs or just accidentally landed on this webinar itself, you are part of the RoboNation family. Speaking of the RoboNation family, we've got one of our longtime sponsors, MathWorks, joining us tonight. Abhishek Shankar is not only our liaison with MathWorks, but he actually has a great deal of experience in the world of where our students are. As a former IGVC student, so that's the Intelligent Ground Vehicle competition that occurs annually out of Michigan. He understands what it's like to participate on a team, to go through the ebbs and flows of building an autonomous vehicle, as well as all the highs and lows at the competition as you have to problem solve and come up with different things. But especially he's an expert now with us in the world of MathWorks, MATLAB, Simulink, and all of the different softwares that you guys need to make your vehicles possible. So without further ado, I will pass it over to Abhishek, who has all the great information on Stateflow. Please just remember that you are more than welcome to add your questions into the chat there on YouTube over the course of the webinar, and we'll get to them in a couple different periods throughout the webinar. And again, thank you guys so much for joining us. Abhishek.
Thank you, Alicia, for that wonderful introduction. Hello, everyone. Again, I'm Abhishek Shankar. I'm with the MathWorks. Today, I'm going to be talking about how you can design and deploy a state machine with Stateflow, which is one of our products along with MATLAB and Simulink. The agenda for today's webinar is going to be an introduction to what state machines are. I won't spend too much time on this because I know from a lot of interactions that I've had with you guys in RoboSub, RoboBoat, and RobotX that most of you are familiar with what state machines are, and in fact, most of you have built state machines with like C++ or Python, or even with Stateflow. So I'm not going to spend too much time on this topic, but I'll definitely give you enough background to so that you can follow along if you don't know what state machines are. The next one, which is going to be the meat of the webinar, is how we build state machines with Stateflow. So here I'll be talking about how you can add states to your state machine, how you can do all the transitions from one state to another, uh, how you can debug state machines, how you can determine why your system is not moving from one state to another, or if there's any error in your system. There are also a ton of other features that you can do. So if you can see in this image, I know it's pretty small, but you can also have like a function that you can call. You can have like MATLAB functions, Simulink functions, or just a state chart function that you can use within your state machine. So there's a ton of new stuff that you can do, and I'll get to that in a bit. And the last part is going to be deploying your state machine. So once you've done designing and developing your FSM or finite state machine, uh, the next step is deploying them to your robot or to your hardware. In this image, I have a robot arm, which is the universal robot arm, but I'm not going to be using that. I'll be using a gazebo world with a turtle bot, just for simplicity. But the workflow remains absolutely the same if you have a physical robot instead of a simulated. So let's start with what state machines are. Just a second. Yeah. So state machines enable you to model different states that a system can have and how it transitions between those states based on sensor inputs or any events that trigger a state transition. So there's a little bit of nuance to unpack here. The first one is what is a state. For a robot, state can mean any number of things. For example, a ground robot, like what we use in IGVC, the Intelligent Ground Vehicle Competition, the states can be as simple as X, Y, and then orientation, right? So you can define that as your state. You can that gives you information on where the robot is located and what direction it is oriented in, which is useful if you want to go to a goal location and plan a path for that. But if you take, for example, RoboSub, that can have even more parameters in your state. You can have X, Y, and theta, the orientation, but you can also have the Z value, which is the height, how deep you are in the water, and you can also have pitch and roll values. So you can have all six degrees of freedom as your states, and you're not limited to just those. You could also add like battery status, for example, to your state. Maybe if your battery status is less than a particular value, you want to go to a state that's called low battery state, where when you're in that state, you want to quickly finish off what you're doing and then get back to a charging dock, or shut down some processes that are not relevant and conserve energy. So basically, state machines let you like develop your autonomy by defining certain states, which the robot would end up in. And to show an example of this, I have something here which is a robot that is trying to avoid obstacles. So you're going to initialize the robot, which will be your first state, which is where it would start when you turn on the system. And then when you tell it to start when you start the algorithm or start like object avoidance algorithm, the first thing it's going to do is go into the state called object detection, which basically is just going to tell the robot to scan around for objects and take the camera input, see if there's an object, and then take decisions based on that output. So if there are no objects, it'll let the robot move forward. But as soon as it moves forward a little bit, it's going to come back. So here you see this transition has um, no condition. So it can freely move between these from move forward to object detection. But to go from object detection to move forward, it has a condition which says that the camera did not identify any object, so it is free to go forward. And again, if there's an object detected, I just have turn left here, so it's just going to turn left and then go back. And then if there are no objects after you turn left, you can just go forward. So this is a simple example of how you can model your autonomy using state machines. So we have different states, and the state parameters for this would just be your x, y, and then your theta. So you just using the position of your robot, and then you're defining your state machine such that it can do the autonomous part by just relying on these three parameters, and then you have like some functions like object detection to process sensor input. So this is what a state machine basically does. It lets you model your autonomy, and it can go from really simple, like the ones I've showed you, to like really complex state flow charts. So those are more used in like a big autonomous system, or even if you have like a semi-autonomous system where one part is done autonomously, and you can have a state machine just for that part. And it's also used a lot in like automotive systems. And you can also use it a lot in aerospace systems where you're like constantly adjusting based on like a million different parameters that might be going on in your rocket or drone. So this is super useful when you want to like manage your system. And you can also with Stateflow, you can like log all the parameters and then see what values are coming out at each time step and log those values to analyze it later. So I'm going to be jumping into building state machines with Stateflow, which is what we're going to spend most of our time in. Let me switch to MATLAB. Right. I have a model already here. I'm going to open that model. So this is a Simulink model with a Stateflow chart that you can see here, right here. And what this model does is it's gonna follow signs in a maze for a turtle bot to go from start to finish. And then so let me open the virtual machine so that I can show you what the environment would look like. Yeah, just waiting for it to load. Actually, let me bring it to the screen so you guys can see it. So right here, I have a turtle bot in a little maze, which has all these little arrows telling the robot where to go. Um, and what we are going to do with the state machine is scan for arrows. And then if it's a blue arrow, we know we have to go left. And if it's a green arrow, we know we're going to go right. So we're going to use that logic to like go from our start position, which is somewhere here, to our final position, which is right here. It's like a small stop sign right there. So that is what we are trying to do. and we have to do this autonomously, right? We are not controlling it with a joystick or any keyboard input. So we're just gonna code something for the robot to go from start to end by following all these signs. So doing this in Stateflow, so I'm gonna move this away so we can focus on the model itself. So doing this in Stateflow is pretty simple. Uh, since this is a ROS2 model, I have to subscribe to some topics. So first thing I've subscribed to is the camera topic because I want to know what the camera is saying, what the signs are telling me to do. And the other one that I'm going to subscribe to is the odometry, which will tell me the position X, Y, and then the orientation. In these little subsystems, all we are doing is taking that ROS message and then converting it to an image. So, ROS message has a lot of like little headers in it. So we are just going to take the image part of it and then send that out for our algorithm to use. So we're going to take just the message.data and then we're going to reshape it because ROS and MATLAB has different ways with which it interacts with images. So there's just a little reshaping to make sure the signal integrity is the same. And we're going to do something similar to odometry as well, which is odometry is going to give you X, Y, and then the orientation in quaternions. I'm just converting it into Euler angles and then taking the Z value, which is the yaw or the orientation, and passing it to this pose variable. So we process these two images right here, and sorry, these two messages right here. We get the image and then we get the pose. So once we have the image, obviously we have a little bit of image processing to do. Right here, I'm just thresholding for red, green, and blue. So if you remember, we have a stop sign that is red, so I want to be able to detect that. And we know green is right and blue is left. And we're going to be looking for these values. When any image we get, we're going to threshold for these values and then see if we find any of these values. So if I just open the script, what it's going to do is do a thresholding based on the mask that we just gave. So it's going to do for red, green, and blue, and then it's going to output the blob size. So if it finds a green blob in the image, it's going to output what is the location of the blob, which you can see. I'm just taking the column value of all non-zero pixels to find an approximate location. And then I'm gonna also use that to find the size of the blob. So if you're far away, the blob is gonna be pretty small, so you don't want to turn too soon. So you want to keep going forward until the blob is big enough, or like the image of the arrow is big enough, so that you can start, processing it to make any decision. So that's the simple logic that I have for image processing. Again, this is simple because my focus here for this webinar is going to be on Stateflow. So I'm going to keep all the other part to a minimum, but I also want to show you guys how it interacts with all the other parts that you have, like image processing, or if you have LiDAR, how it can work with all the LiDAR data that's coming from the robot. So that's like the pre-processing part of it. So you have an image, you have like two messages coming in, you process it, and then you get that value into your main decision-making chart, which is our sign tracking logic. So this is the main state flow chart. So if you look here, we have these little boxes here. These are what we call states. So this state, for example, is called scan for object, where if a robot is in this state, it's not going to have any linear velocity. It's just going to look around. It's like turn in place, look around, see if you can find the arrows that we're looking for. So this is basically the init state for the robot. It's just gonna, if it can find a sign is just going to stay in place and keep rotating till it finds something. And once it finds something, you take a transition. So this arrow is called a transition. And how you know that it finds something is that the blob size of what the color thresholding app returns, that will tell you that if the size is greater than 20, again, that 20 is an arbitrary value that I set based on, all the experiments that I ran. But you can play around with that value. But if it's greater than 20, we know that it detected a valid uh, thresholded blob, and we want to go into the track object state. And the track object state, basically what it does is it'll move forward if the object size is really small. So if the object size is less than 110, for example, it is just going to go forward with a velocity of 0.15 meter per second. And if it's like really close, if it's greater than 150, then we are going to go back because we don't want to be like, kissing the wall essentially. We want to be like little further behind, so that we have room to turn. So we're going to go back a little bit. So the sweet spot is between 110 and 150. So when it's in that range, it's going to give, it's just going to stay in place. We know that we are at a position where we can take a decision. We can either turn or we can, go somewhere else if that's what the logic decides. So that's for the linear part. And then for the angular part, what I'm doing is taking the location of the blob and seeing if I have to turn left or right. So if the blob is to the robot's left, I want the robot to rotate clockwise so that blob is centered. Or if it's to the right, it's going to rotate anti-clockwise so that the blob is again centered. Again, we are doing this so that we have the robot and the signs oriented in the right way. We don't want the robot to be too far back or rotated at a different angle when we take a decision. So that's what all of this does. And then we are gonna once we know that we are at a place where we can make a decision, so it's at the right angle and then it's at the right distance from the sign. Um, we are going to check if the angular and the linear velocity are zero. So these are conditions. If these two are zero, we're going to go into turn in place. Oh, actually, we are going to check if index is equal to 1 first. This is again checking if the object was red. If index is 1, object is red. If it's 2, then we know the object is green and we have to turn in that direction. And if it's 3, we know it's blue and we have to turn the other way. So if it's 1, we're just going to stop and then stop the robot. We're going to set all the values to 0. But if it's not stopped, we're just going to go to turn in place. And then we are going to turn to the direction that we have to go. So right here, if you see if the index is 2, we are going to turn right or anti-clockwise. And if it's blue or if it's 3, we're going to go left. So that scan direction is set here. And once we go there, the turn in place state will make sure that the robot doesn't move forward, but it just turns in place. And we're going to keep turning until the difference between the current pose and the pose after we turn is greater than 60 degrees, so pi by 3. So we're going to wait till it turns at least 60 degrees before we go for um, scan for object state again. So this is like the high level of what the Stateflow does. So I will be going into the details of it, like what are these EN and DU that you see here, and how do you set like these state transitions and how the Stateflow essentially works from time step to time step. But before I go into that, is there any questions that you guys want me to address?
Yes, we have two questions right now. The first one says for hierarchical state machines in Stateflow, for complex mission autonomy like dynamic retasking mid-run or handling emergent behaviors, what best practices would you recommend for balancing readability and execution efficiency when deploying to embedded hardware?
That's a great question. So especially for bigger state machines, like you said, when you have multiple hierarchies, one of the best thing that you can do is have like multiple subsystems. so that it is easy to read. So you can have, for example, if I go into modeling right here, I can insert like a subchart, which will just do like one part of it. So if, let's say you are suddenly going into a low battery state, so that could be an entire subchart of its own where it takes care of what to do if you're in the low battery state. And you can also do things like, if you see here, we have like Simulink functions or MATLAB functions, um, things that you can use to basically break it into smaller pieces that you can work around. So this is, um, to tell it to you in coding terms, this is more like coding with like different functions or making it smaller chunks so that it is readable, it's easy to maintain, and you can also assign these different things to different team members. So if usually in a large subsystem you have like multiple people working on it, so you can tell like one person or like one sub team to like work on your battery processing or work on the object detection part or autonomy or things like that. So breaking this down is the best practice that I can recommend, especially for larger system, because if you just have like a huge chart, it's going to be a mess and it's going to be really hard to debug if something goes wrong. Is there another question, Alicia?
There is one more question. How does it handle asynchronous sensor inputs or unexpected environmental triggers?
Right. So there's actually reacting to asynchronous input is pretty common in Simulink and Stateflow. So we are built for that. We process all the data. So for example, the odometry is coming at a different rate than what camera image is coming in. So camera image, I think, is coming in at 30 hertz, but the odometry comes in at a particular, frequency. I think it is for 50 hertz. I'm not sure, but they're definitely not the same. So we have sensor data coming in different areas. So what we have is something called the enable block. So for example, we want the image processing to happen only when a new message comes in, not when a new ODOM message comes in, only when a new camera image comes in. So all these subsystems react to the sensor data that's coming in, and then the logic here also reacts at the time set that we decide. So usually you would decide it at the processing time should be such that the entire machine can run in that time. So your embedded system should have the resources to do it. If you set your sampling time to like 20 milliseconds, you should be able to execute this track in 20 milliseconds, which is pretty easy for any modern board set. If you're using like a Raspberry Pi or Jetson, 20 milliseconds is a lot of time to do a simple chart. But again, if it's a complex hierarchical chart, you want to make sure that you give enough time for that execution to take place, and also ensure that that time is not too big that the robot would not be able to like follow that autonomy because it is going too fast, but the execution time is too slow. So you got to balance that based on your robot specification. But asynchronous values can be easily handled in Simulink and Stateflow. All right. So I'm going to be moving on to like some more details on how the state chart is built. So the first one is these two different brackets that you see. So there's this curly bracket in transitions, and then there's a square bracket in transition. So in Stateflow, this syntax basically means that a square bracket is a condition. So you take this transition if this condition is true. Whereas a curly bracket is you're setting output. So when you take this transition, you're going to set the scan direction to 1, which is clockwise. And then you're going to set stop robot variable to false. So, it doesn't stop as soon as it initializes. So that is your output that you set when the system is taking that transition. And all the conditions are checked when a robot has to move from one state to another. So every sample time, so if my system is running at 20 milliseconds, so every 20 millisecond, if it's in scan for object state, it's going to look at the exit transition. For example, this has only one. So it's going to look at the exit transition and check if this condition is true. If it is true, it will switch to that state track object. If not, it's going to stay at scan for object. Um, if you're in this state and then you have like two exit transitions from this state, what it would do is you can assign priorities. So the first priority here, you can see the number here. It's going to check this one first. So actually, this has three because it branches into two other exit conditions. But you're going to check this one first, and then you're going to check this one first. If checked if the index is one, and then you go to the state. But if this is false, you will take this one. But if the main condition itself is false, you're going to go back to scan for object. So that's basically how the state chart works. And again, it's pretty easy to model in Stateflow because state machines essentially are like diagrams that you make. So these are things that you do in the design phase of your robot. So you come up with the design, come up with your autonomy and what your system must do. And usually those are like block diagrams that you draw in your whiteboard to explain to your teams. Um, Doing it in C++ is also possible, but then you would have to code that block diagram into your C++ code, which can be one, time consuming. The other one is error prone. So you might make small mistakes when you're trying to translate a picture into a code. But what Stateflow allows you to do is you can just take that diagram and then basically replicate it in Stateflow. So for example, if you want to insert a state, you just go here and then drag this then, and then you have a new state. You can just name it whatever you want. And then you can like assign transitions to it. You can also like set a self loop. So if you're in that transition, you're just going to be looping in so this could be useful if you want to have like a counter. So you want to count for 10 cycles before going somewhere. So that is a self loop. But you can also like assign transitions from like, for example, I want to go from this state to this state, scan for object to, let's say, a test state. And then you can design what condition that it would go into. So you can set some value, set some condition for this. So let's say if stop robot equal to true, you want to go to the state. Um, just gonna move this here so it's easy to read. We're gonna go to test state. Yeah. So that is one way that you could do it, and then again, you can also set like output. So if stop robot is true, we want to set b equal to 0. Sorry, b equal to 0 and w equal to 0. So we want to set these conditions if you're taking this transition. So that's how you would transition from one state to another, and also set conditions and outputs. So I'm gonna delete this because yeah, because we don't need that. But that's how you would do it. You can easily drag states and then add it. And the next one that I want to talk about is these. Oh, didn't mean to do that. These en and du that you see here. So what en means is entry. So this is telling the state to set these values to 0 and 0.25 times the scan direction when the system enters that state. So as soon as it enters, it's going to set it to these values. Um, du is during. So every time um, the system is in that state, it's going to do things that are in the during part of that state. So for example, in the track object state, we have all this set to both entry and during. So it's going to do it as soon as it enters, but also in the next sample time when it's still in that state, it's going to do the same thing again because we want to keep updating our blob size for the arrows and also the location. So we want to keep constantly updating every time a new value comes in. So every sample time it's going to keep checking it and then assigning these values based on that. So that's how entry and during works. And you also have exit, which is something that which is something that you can use if you want to set some values while you exit a state. So you have three different things that you can do when you're in the state. You can set something when you're entering a state. You can set some stuff when you're in the state, and you can set some stuff when you're exiting a state. So just to repeat, the entry statements will not work if it's in the state for more than one sample. So for example, if I remove the during part here, it's not going to execute any of this in the subsequent sample time. It's going to take what the value was when it was first entering the state, but never updated based on the new camera value. So you want to make sure that whatever you choose, entry or during or exit, reflects what autonomy that you want to make. So those are like the next level basics for Stateflow, how to add transitions, how to set conditions, and how to set outputs, and also in-state parameters that you want to set using the entry, during, and exit function. So once you have all this, the other one that I want to touch upon is Model Explorer, uh, which basically defines all your state and also all your input variables, output variables, and local variables. Excuse me. So these are pretty self-explanatory. So inputs are your inputs to your state chart as a whole, not just one state, it's your whole chart. And outputs are again outputs from your chart. And then local are some variables that you're just using locally in the chart, but it's not like something that you would have to output necessarily. So that's how you decide all the scope of your variables. So if you want to add a new variable, what you would do is you would make the chart, you would have like new values, and then you can have like if you right here, if you see there's an option for add data, which would add like a new variable to your state chart. I'm gonna delete this. But that's how you do it. And this is important because this chart must know what are the inputs and what are the outputs. And you can also define like data types. So this is going to inherit from Simulink. So since it's coming from a Simulink model, it'll inherit the data type that comes from that. But if you want to be like strict and then decide that this is going to be an integer or this is going to be a float value, you can also set that over here. So if I scroll down, you see all these different options that you can set. The same thing with size. You can inherit -1 means that it is inheriting based on the upper levels of the chart. But if it's like a matrix that you know the size of, you can always input the size over here. So that is the Model Explorer, which is the next part, which is super important when you're trying to design a state machine. And there are like some code gen stuff that you can look up. Here, there's like some options, which is pretty advanced, so I'm not going to go too much into it. But some things like support variable size array or saturate on integer overflow and things like that are pretty standard. These are by default, but they're checked. But if you don't want, you know that you're not going to have any variable size arrays, you can always uncheck this. And if you don't want to saturate, if you want to roll back on overflow, you can uncheck this too. So these are some options that you can play with. We have extensive documentation on these. So if you just Google Stateflow and MATLAB, you'll have like tons of documentation pages explaining all of this. But again, you can also reach out to me through email or Discord if you have any question on any of this. So that is the essence of how you would build a Stateflow chart. Um, there are like even more things that I would like to cover, but I don't think I would have enough time to go into deployment as well. So, but I'll quickly touch on these. So you can have, for example, a Simulink state or more importantly, you can do like stateflow function or MATLAB function. Um, so this is again, you can give a name for this function. So, I can just do get direction or something like that, and then set like a logic here. And then whenever in this state, I can call that function um, to like, do this part. So I can do all the if index equal to 2, scan direction, all that stuff as a function instead of having the loop right here. But since this is pretty small, I just put it up as it is so that it's not too confusing. But as one of the questions came up, if its model is huge, you really want to make sure you use these functions so that when someone else is coming and looking at your model, it's pretty clear what you're trying to do. And it's not like a huge model, which is super hard to follow. So that's what you could do with state machines. And now let me just quickly touch on the output before I run the model and show you how it works. So you'll be taking the linear and the angular velocity and assigning it to the command well um, message topic. Again, the message is going to be geometry message twist. So if you're familiar with ROS, you know that this is the message type that you use for sending command velocities to your robot. And then if the robot reaches the stop robot sign, you're going to stop the simulation and make sure that it's not running unnecessary because it has reached its final destination. So with that said, let me pull up the virtual machine again. Oh, sorry, it came up on a different screen. Um, okay, so hold on. Let me close this and then start it again so that it's reset into its first position. I'm gonna do deeper Rust maze. I could have just moved the robot back, but in a virtual machine, sometimes Gazebo is not the most fun to work with. So closing and starting again works. All right, so we have the robot back at its original place. So what I'm going to do is go ahead and run the state machine. Let me make this smaller so you can see everything. And I will run it. So now the robot is running. You can see that it is moving. Let me bring up the camera feed as well. So you can see that it's moving forward because the blob size is pretty small and we are telling it to move forward. Let me go into the flowchart, the state machine, and you can see that it is in this state because it is highlighted here in like bright blue. You can't miss it. So now it has come somewhere here and you can't see the object again. So it is scanning for objects now. So, but as soon as it sees it, it's going to go back here. It's going back a little bit to adjust, but it's doing its stuff, and then now it's going to turn and follow the sign. So this is how you can really see what's happening or like what's going on behind the scenes, what the robot is doing. So it's super easy to debug. You can see that it's all the transition that's going. You can see where it is right now, what state it is in, what it is trying to do. So it is taking this part, which is setting the velocity to 0.15. So it is going forward. Um, so all this is super easy to like inspect and make sure that the robot is running as expected. But the other thing that I want to show you is how we can set breakpoints. So, for example, right here, if I want to like set a breakpoint to see if it's taking this transition, what I would do is click on this transition properties, uh, sorry, transition tab, and then add a breakpoint. Oh, sorry, I can only do it before I run the model, so I'm going to stop it for now. And then I'm going to add a breakpoint. So you can see this red circle. That means that there's going to be a breakpoint here. And I can also, actually, let me remove this breakpoint. And then add one here. Set breakpoint. And then I'm going to change this condition to blob size greater than 200. So obviously this is wrong. The blob size is never going to be like 200. So for example, if your robot is stuck in the scan for object state, then you can see why that is happening. So if I run this again, so you can see the robot is already spinning because I stopped it abruptly. And then the last value that it was sent out is for just the angular velocity. So it's just spinning because it doesn't know what else to do. But yeah, so yeah, I have this over here. So you can see that it is actually never going into this transition. Um, so the one thing I can do is click on this and then check this. So this will check when the transition is tested. It will stop it. So here you can see this green line, which means it is trying to see if the transition has been like achieved. So you can see that the blob size is the maximum value is 13. So it's not gonna, you know, take that value. So I can just continue and it's gonna stop again because it will stop at every time step because that's what it does. It keeps checking every time step. Right now it cannot see the image because it is rotated differently. So I am gonna change it to only when valid. And where's that figure? Yeah, oh, we can see now. So if I continue, you can just see that the blob size is going from like 40, but it's never actually going to reach like 200 because it is just too small. Um, yeah, sorry, it's just too big for the robot to like see. Actually, let me put this over here. And then, yeah, you can keep seeing that it can see the tiny arrow, so it's going to be small, but it never saw like the big one. And the big one is right now at like 40, but again, it's not greater than 200, so it's just going to be stuck here. So this way you can easily identify why it is stuck in the state, and then you can stop it and set it back to the value. Set it back to 20. Start again. I still have the breakpoint here so that you know when this transition takes place. Right. So this running again. Um, this is the old feed. Okay, so it has found it. Then so I'm gonna remove the breakpoint here and continue. Um, okay, so it is still turning because I was too slow to remove the breakpoint. Hold on, where is that? Yeah, for some reason my camera was not updating. But yeah, now we can see, and then you can see that this state is highlighted because it took the transition, and it's right here. And again, this is true, so I am gonna clear this breakpoint and let it continue. So essentially, it's super easy to follow along what's going on and then see how the robot is doing. So once we have this, I'm gonna stop it uh, because I just realized I only have 8 more minutes, which is maybe just enough time to go to deployment. All right, so before I go into deployment, any quick questions, Alicia?
Yes, we have one more question. It states, when implementing nested or parallel states for mission level autonomy, how do you
Mhm.
recommend managing shared data or interstate communication, especially when targeting deployment to resource constrained embedded systems?
Yeah, so parallel states, for data that you're sharing between states, I would always recommend not inheriting data when you like. So, for example, when you go to the um, sorry, model inspector, you want to make sure that all the data that you have is not inherited, and you specify the data type and the data size so that your the code gen will make sure that all the data is as expected, especially in a resource constrained system. Like you said, you don't want to have like variable size arrays, or you don't want to have things defined to be a much larger size than it actually is. So you want to ensure all of that is taken care of. And for like parallel states, similar Stateflow would automatically make sure that uh, the data shared is pretty optimal. So it's not it'll make sure that you can like trust it to take care of the data in the backend. But if you have any specific issues with that, you can always like reach out to me. And because it is hard to like say what is the best practice if I don't know what the use case is, because this is super dependent on the application area. So for automotive, for example, you have like different things to consider, but for robotics, there are like some other things that you want to consider. So it depends on the application, but I would recommend like setting values here, especially if you're putting it to an embedded system. Right. So sorry I had to move so quickly from your question because just very little time. I also want to touch on how you can deploy it. So I'm gonna first, before I deploy it, I'm gonna actually stop this model. Um, so I'm gonna stop it, and then I'm gonna go to ROS. And so I know the IP address of my virtual machine, but if you have a robot running with a Jetson or anything, you can take the IP address from that and then pass it to it as well. So for example, my IP address is right here. So I'm just gonna put that value here to the remote device and then do test connection. So this is always recommended before you deploy your code. You want to make sure you can ping that system. You have the write privilege so that you can transfer the code, and all the workspace and everything is like proper. So you have to give like username and password. So if you go to manage remote device, I've given the username, password, what's a ROS2 folder, and then what's my workspace. So once I have that, there are different options. You can generate code, you can build model. So generate code is just going to generate C++ code for you um, that you will have to transfer and then like build it. Build model would generate a standalone program and then deploy it to the ROS device, but it won't start it. It'll just transfer it and then build it for you. And then build and run is going to generate, deploy, and then start your model. So for this case, I'm just going to do build model. So it's going to generate the code and then uh, deploy it. So then we can close MATLAB and then just work on our virtual machine. So let me do that. So if you look at the diagnostics, you can see what's going on. But while this is going on, if there are any other questions, I can take them as well, because this will take a few minutes.
We don't have any additional questions now.
Okay,
But guys do have any questions, feel free to put them in the chat.
yeah. And also, while this is going on, I'll make a quick announcement um, for RoboSub, especially, because we are excited to share that we'll be doing a MathWorks Simulation Award this time at RoboSub. So if you guys have participated in RobotX, we did a similar award for RobotX. We saw like teams showing their model, their robots, and then all the awesome stuff that they did with MATLAB, Simulink, or Stateflow. And we actually just recently published a blog with Lake Superior State University that won the MathWorks Award at RobotX. And I can post that link in chat if you guys want to go take a look at what they did. Alicia, do you have the link with you?
Yes, I can go ahead and put it into the chat right now.
Okay, thank you so much. But yeah, so we're going to be doing a similar award for RoboSub. So if you're participating in RoboSub, which I highly encourage you to do so, because it's one of the best competitions for underwater robotics. And if you're participating and if you're using MATLAB, we encourage you to participate in this award. It's totally optional, but it gives you a good like a good exposure to the MathWorks community, and you also stand to gain all these award prizes. And like I said, you get a post with the MathWorks Student Lounge, which is read by a lot of people within MathWorks and also by a lot of companies outside. So it gives you that exposure. And all you need to do to participate is just do like a 5-minute video on how you use MATLAB or Simulink or Stateflow or any of our products to solve a particular problem you face. So it is super easy to get into and super easy to do it. So there's nothing extra that you have to do to participate in this. If you're just using MATLAB or Simulink, all you have to do is tell us how you used it and you are in the awards. And we'll judge and we'll give you the prize money if you end up winning it. And the deadline is July 11th. Sorry, I didn't mention that, but I think this is in line with all the report deadlines that you have for RoboSub already, or it's a little later than the report deadline.
We've given you guys a little bit extra time. So make sure to check out your email. You will have received an email with some additional details, and we'll be posting more and sharing more about that in the coming months. But yeah, we're excited and we're very grateful that MathWorks is doing this. This is a great opportunity to build your resume, practice more of those soft skills, and just share some of the really cool stuff you guys are doing with your machines.
Yeah, totally. So for me, the build process failed, which is new because it didn't happen before. Let me see what the error is. Okay, so this is because of a Cortex API, which is a Quinoa robot arm thing, which is, I don't know why it's interfering, but let me see if I can build and run. So it was able to generate the code and transfer it, but it failed to build because I think it clashed with some of the other additional packages that I have installed for a Quinoa robot arm. But I mean, you shouldn't be running into those issues, but just in case, I'm sorry it's going a couple of minutes over time, but hopefully this one works and I can show you the build code that you can run in your ROS machine directly. Always a new error, and it happens exactly when you don't want it to happen. Right? All right, so here you can see that the code generation was complete, took like 5 seconds for it to do that. And now it's using Qualcomm. Okay, so now it's transferring the code to my ROS device to this location. Right, now it's starting the build process. Right here and start the maze. So in case it starts running, make sure that it has the maze open. Oops, too big. Yeah, my PC is not being very helpful right now. Right. Okay, so we have this over here. Let's see what's going on with the model. So right now it's trying to build the assigned following robot ROS2 model. Just, I mean, the ROS name is going to be same as your Zoomling name. So make sure you know what's happening. So you can see that Qualcomm build was successful. It was able to do it. So now you should see. Um, oh, the speaker. So now the robot is running because the code was built and it's running in ROS. So you can actually go ahead and close Simulink. So I'm not going to save it. I'm just going to close it, and you can see that it is still going to keep running um, because it is not running from MATLAB anymore. It's fully in your system. To ensure that, you could also go to your files. If you go to ROS2 workspace, go to source, you can see the sign following robot is right here. So all the code was transferred. And actually, what I can do is you could also like open a new terminal and then run it as how you would run any ROS2 node. So you could just do ROS2 run sign following that name. Yeah. Yeah. So you could just do this and hit enter and it would run that node again. So yeah, that's it. The robot has reached its final position and it had stopped. So that's how you would do, that's how you would model and deploy your state machine with Stateflow. If you have any questions at all, again, please feel free to reach out to this email here. That's my email. And you could, I'm also in the RoboNation Discord. So if you have any questions, you can just tag me in any Discord post and I would get back to you quickly. But if you don't have any questions, I think we can end the webinar now.
Amazing. Like Abhishek said, feel free to send an email over to him in that email he has on the screen. We've also put it in the chat. We've also added our RoboNation emails into the chat as well. So if you're curious about any of our competitions or events or programs, things like that, feel free to reach out to competitions@robonation.org, or feel free to reach out just generically if you're interested in RoboNation and sponsoring and partnering and learning more about who we are as an organization, to humans@robonation.org. Again, those are all in the chat as well as in the description. And we're so grateful that you were able to join us for this For this particular webinar, we have one more in our MathWorks mini series. We're sad that we are coming to a close with it, but we have one more mini series that we have next month on June 10th, where we'll be talking about determining the direction of arrival from an acoustic beacon. So make sure you bookmark in your calendar to join us for that, and we look forward to having you then. Thank you all for your amazing questions. We look forward to seeing you next month. Bye-bye.